We're now continuing on with Chapter 2 in our solution of linear systems, and you'll recall that we are looking at the two different approaches to solving linear systems using direct methods and indirect methods. And in this lesson we'll be looking at direct methods and a couple of different formulations of them. Three methods that are used in scientific computing. One you'll be very familiar with, Gauss elimination, which is typically the approach taught in Math 251 in linear algebra. In that formalization of solving the linear system AX equals B, again, A is the matrix, is coefficient matrix, and B is your right-hand side vector, and X is the solution vector you're trying to solve for. Typically what you do in these systems is you try to reduce the original system of equations into another form. In this particular case, the final form is usually an upper triangular matrix where the right-hand side has been slightly perturbed. Notice that it's in this table that we changed the system AX equals B to a final form UX equals C, where U is an upper triangular matrix and C is also a right-hand side vector, but it's not necessarily the same as the original right-hand side vector B given in the original problem. The idea is to use those row-wise operations so that the solution doesn't change. Hence, you still see the same X that you saw before from AX equals B to UX equals C. So the solution is preserved, but it's easier to pull off the components of X when your matrix has a very nice form, which is illustrated right here. So LU decomposition is a different way of looking at Gauss elimination in the sense that you're transforming the matrix. But the difference here is that you're actually trying to find a different way of factoring the original matrix A into two factors L and U so that you could solve LUX equals B easily as opposed to the original system. And then finally, what's called Gauss-Jordan elimination is an approach to totally take the original system of equations and reduce out completely the solution X. In this case, the identity times the matrix X is the same thing as the original solution vector X. Basically, what you're doing is finding the inverse of the matrix in this approach. The first two are the two that we're really going to look at seriously and comprehensively in this chapter. Gauss-Jordan is a little bit too costly for most large-scale problems. Although theoretically it's very nice approach to use, but I think computationally it's too expensive. So we're going to start off with just what do I mean by what U and L mean in terms of these final forms that you see here for Gauss elimination as well as for the LU decomposition. And I'm going to do it in the form of 3x3 matrices. So a sample upper triangular matrix U might look like something like this. Again, for a 3x3, what you would have is a components, say in the first row, and I'm going to use indices here to indicate that we have rows and columns. I'm having a little problem here getting the subscripts here. So again, we have U, 1, 1, and then we have U, 1, 2 going across the second row, and then finally across the first row for a 3x3 would have U1, 3. So those are the three components in the first row. For an upper triangular matrix, everything below the diagonal is 0. So, in the next row you would have a 0 component. And then on the diagonal, we'll say we'll have another element. We'll put it in the 2, 2 position, U2, 2. And then we'll finally have the last element in the second row is U2, 3. Again, that's just indicating which row and which column, not doing zero indexing here. But because it's an upper triangular matrix, the last row here would be all zeros, except for the last component in the diagonal in this case. Would be U3, 3. Get a 3 there. So what we have here is what we call an upper triangular matrix. Everything below the diagonal here is 0. Okay, this is just a 3 by 3, but it gets an illustration of what we're looking at. So in doing Gauss elimination, we're actually finding an equivalent solution instead of solving a dense matrix Ax equals b, where the matrix A has all the elements provided with very few, if any, zeros. This matrix here has a very nice form that'll make it very easy for us to pull off the solution one component at a time. The third component, then the second component, and the first component, because of this triangular structure. And we'll see that in just a minute. In terms of what the indexing would look like for a lower triangular matrix, we could call this matrix L. I can get the pen to behave here. So the lower matrix L in this case would be another matrix, and since it's lower triangular, what that would mean is that you would go down, say, the first column, L1, 1, then L, in this case, going down the first column, we'd have 2, 1, and then we would have L3, 1. But then when we go across the first row, because it's lower triangular, you would have zeros in those positions, and then the middle diagonal will be L2, 2, and then a 0 here, and then at the bottom row here you'd have L3, 2, and then L3, 3. And that would finish out this matrix. So again, this is lower triangular in the sense that get rid of that. A little selection problem here. We'll just move that out of the way. So again, what we've got here is a lower triangular matrix where all the elements lie below the diagonal, versus over here in the upper triangular matrix, all of the elements fall below the diagonal. So that's what we mean by an upper triangular matrix and a lower triangular matrix. Okay, and again, this is only for a 3 by 3, but I think you get the gist of it, that anything below the diagonal will be assumed to be 0 for the U case, and for the L factor, everything above the diagonal would be assumed to be 0. So let's look at LU decomposition, just to understand how those L and U factors are used before we go into examples, a specific example demonstrating Gauss elimination as well as LU. The idea behind LU decomposition, which is commonly used in scientific computing, it's a more efficient way of solving linear systems, is again to transform the original linear system, Ax equals b, to this particular form, A equals LU first. In other words, you're factoring the original matrix before you even begin to do the computations to find x. So the goal is if you can factor the original matrix as the product of this lower triangular times an upper triangular, then you can solve the original linear system Ax equals b as indicated here. We would actually think of substituting that factored form in for A. And so now what we're solving is a factored form of an L matrix times a U matrix quantity times the solution vector we're trying to find equals B. But what you can do initially is to look at some ordering here and say, well, let's just look at the fact that you've got two matrices times the vector, and consider, for example, the fact that that's equivalent to the lower triangular matrix L times this quantity, U times X, quantity equals B. So that if we made the substitution that, let's just say for argument that U times X is equal to a vector Y, whatever U times X is. If we could figure out what the Y is, then we could solve Ly equals B, all right, by what we call forward substitution, and then take that Y, if we could get Y, and then what we call back substitution for the solution vector X. So again, what we would then do is a two-phase thing. We would take the original right-hand side vector B and solve a system Ly equals B using the lower triangular factor from the original matrix A. That would be the first part. Solve for that Y again, and then use that Y as a right-hand side for this other set of equations called Ux equals Y. And then by solving that for X, you have the same solution of the original linear system that you had before, A times X equals B. Now this may seem more complicated, but this will be efficient only if the solving of the Ly equals B and the Ux equals Y is so much more faster and efficient than it would be to operate with all of the elements of the original matrix A. And it turns out that's exactly the case. So I'm just going to illustrate what this would look like for a 3x3 linear system, and I'll just do the indexing for a general problem before we do a specific example, just so you see what we're talking about. So let's go back to our 3x3. If we were solving this Ly equals B, then essentially what we would have is we would go back and look at our indexing and say we would have L11, and again, let's finish out the representation of our lower triangular matrix like we had before. L21, L22, doesn't look good there, 0, and then the last row would be indexed L31, L32, and L33. Again, these are just general placeholders. Sort of in designing an algorithm, it's good to just sort of do it in a generic way before you would even code it or program it, so we kind of understand what the operation's going to look like and what the complexity of solving problems is going to be. And again, let's index the Y. Again, there's just 3 components because I'm just solving a 3x3. So let's just represent the Y matrix this way, excuse me, the Y vector this way, and then set that product equal to the original right-hand side. Okay, that's a 2. There we are. Okay, so what we have is a representation of Ly equals B for a 3x3 case. But here's the deal. The special form of that lower triangular matrix, if you were now to go back and think about what matrix vector multiplication, how that works with your linear algebra class in 251, again, what we would take is the inner product of the first row and the solution vector y there and set that equal to b1. Well, if you did that, because of those 2 zeros right there, all you're going to get when you do that first inner product is you're going to get L11 times Y1, and I'm going to skip some spaces over here. That's just going to be equal to what? B1. Again, how did I get that? You're doing the inner product. That means L11 times Y1 plus 0 times this plus 0 times that. So the 0 components annihilate anything to do with Y2, Y3, and all I'm left with is L11 times Y1 equals B1. Do the same thing for the other 2 rows. Then you would have L21 multiplied times Y1. But now you're going to add this other component plus L22 times Y2, and that combination, or that linear combination, is going to be equal to B2. Again, the 0 in the last position of that second row will be multiplied times Y3, and that's why there is no Y3 component. But notice something. You could quickly solve for, Y1 easily because you would just divide through by L11 and you'll get Y1. And then if you have Y1, you could substitute it in here and you'd be able to figure out Y2. And that's the pattern. You can pull off the component of that Y vector, a new component on each step. Let's go ahead and write the last row. L31 would be multiplied by Y1. You would then add L32 times Y2, but then you would have to add L33 equal to B3. And again, if you had Y1 and Y2, you would be able to immediately obtain Y3, and I forgot to add it in here, so this should be y3 there. Multiplied by the L33. You would be able to pull off that y3 immediately. Okay. So let's go ahead and represent what that would look like. Again, what we said earlier is that you could immediately get y1 by dividing through by L11. So you immediately pull off that y1 is equal to b1 divided by L11. And then you could get, once you had y1, how would you solve for y2? Go back to this second equation right here. Just go right here, look at this, and say, gosh, if I had y1, then I could push everything, I could multiply y1 times L21, push it over to the right-hand side, and then what I could get is that y2 then would be b2 minus L21, y1, and that quantity is the y1 here, that quantity would be divided by L22. And then lastly, you could see if you have computed y1 and y2, then you could substitute them in the last row. And finally, what we would get for y3 is we would have to have in parentheses b3 minus two products. You would have minus L31 times y1 minus L32 times y2. That quantity would all be divided by L33. So again, you're pulling off every component of the y vector one at a time. You get y1 first, substitute in the second row there, get y2 and y3. Why was this easier? Because we had that nice lower triangular form. You can pull off one component of y at a time. Okay, now since we have the y vector, remember, in solving a linear system ax equals b using the LU decomposition, we've used the L factor. Now we need to use the y factor to get the x vector. We're trying to solve, in this case, once you have y, we are trying to solve u for ux equals y, and we will have the solution vector y, x that we see. Y is just an intermediate vector that we have to determine, and that was based on solving L y equals b. So let's represent graphically what we're doing this time. We're solving ux equals y for a 3 by 3. So let's represent the components of the matrix. Again, we're going across the first row. Then we go representing again our upper triangular matrix. So the next row we have a 0 in that position, then the diagonal element u22, u23, and the last row everything is 0 except for the diagonal element. Everything below the diagonal is assumed to be 0 for an upper triangular matrix. This is multiplied by what? Representations of the x vector, which is the solution vector we're trying to find. It's the second phase of the LU factorization process and solve process. Now what is this equal to? Now some people might think, oh, don't you put the b in? No, no, no. We're trying to use that original y vector that we just found, so we're going to put y1, y2, y3. Remember, the original right-hand side was used to solve Ly equals b. Now we're just going to go to the same argument we did before. Find out represent what this matrix equation really means in terms of the inner products of each row with the column vector x, and set that equal to the corresponding component of y. So let's just do that. So you'll have u11 times x1 plus u12 times x2 plus u13 times x3 has to be equal to y1. Again, you're multiplying. This is the inner product, so you take each component of this row with this vector, multiply each of the corresponding components in order, and then add them. Go to the second row. Now that 0 is going to multiply times x1 and get 0, so we won't have anything in that position that involves x1. So all you're going to have here is u22 times x2 plus u23 times x3, and you'll set that equal to y2. And then finally, you see what's going to happen. This very nice form is going to, when you multiply 0 times x1 is 0, 0 times x2 is 0. So the only thing you're going to have when you do the inner products here, in this case, is u33 times x3 equals y3. Now, this almost looks like what we just had before in the previous slide for L, but now it's sort of flipped over. You're not going to immediately be able to pull off x1 and then x2 and x3. It's going to happen in the reverse order. You can immediately see that I can get x3 very simply. I can get the last component of the solution by just taking y3 and dividing it by u33. Again, these are just real elements. U33 is just some real number, and dividing it into y3. And of course, we're assuming that u33 is not 0. You might easily be able to determine that if u33 was 0, you can't. That the solution's not. There's not going to be a unique solution. You would have a singular matrix. If you factored it and that u was 0, then you've got a singular matrix. You're either going to have an infinite number of solutions or no solution at all. In this case, we're not going to worry about that. We're going to assume it's not 0. Now, if you had x3, you can plug it into the second row and pull off x2, and then now you see what will happen. You get each component of x in reverse order one at a time. Well, let's go ahead and just write it out so we understand how we would get it. x2 would then simply be what? Well, you would have x3. That would be known. So this component would be pulled over to the right-hand side. So this is going to be equal to, in parentheses, y2 minus u23 times that x3 that we now know. That quantity would be divided by u22. So once you have x2, x3, you could plug them into the top equation, and we would pull off the final solution component. x1 would be, in parentheses, y1, which we would know, minus u12 times x2 minus u13 times x3 quantity divided by u11. So this is an illustration of the process it would take if you had an LU factorization to determine the final solution. So this is the final solution vector, but just the elements were computed in reverse order. You get the x3 first, then the x2, and then the x1. Now I'm going to show you an example of using LU decomposition on a 3x3, but now have actual values for the matrix A and the right-hand side B. So let's suppose that we are solving the linear system AX equals B, and what you have below are the actual components of the 3x3 matrix A and the right-hand side of vector B. So I'm going to go ahead and show you what the factorization of A would look like. If you were to factor A into an LU, you could show that the two factors could look like this. So those are the factors of A, where first we have L. I'm going to show you what U would look like. Remember, L is lower triangular, U is upper triangular. So 0, 0, 2. So what do we have here? Lower triangular matrix L is indicated here on the left. Upper triangular matrix upper triangular matrix U is here on the right. Notice that below the diagonal is 0 here, above the diagonal is 0 here. If you were to multiply L times U, you would reconstruct the original matrix A. Again, the idea is that, but if we can produce a code or an algorithm that would take it, or any matrix that we had A, assuming it's non-singular, we could factor it into an L times U and then use those components to solve the original linear system. So what we're going to do now is just go through the process of doing that like we did before, just so you have an illustration of how to do it. And so again, what do? We have to solve two subsystems. We have to solve Ly equals B, followed by Ux equals Y. So that's the process. Again, we use the vector y as an intermediate form. It could really be called anything else, z, h, anything. It doesn't really matter, but we just use it as the intermediate solution here to the lower triangular system, and then use it to finish out solving for x. So if we were to represent the problem, we could do that. Let's do Ly equals B. So we know what L is now. 2, 0, 0. Minus 1, 2, 0, 1, minus 1, 1. And again, let's represent as and index it appropriately. Y1, Y1, Y2, and Y3. Close the vector. What does that have to be set equal to? The original right-hand side B, 28, minus 40, 33. So now that you have the representation of it, we would just go through the same process we did in the early example for generic representations of the components. Now we have actual values. If you were to take the inner product of the first row, 2, 0, 0, with y1, 2, y2, y1, y2, y3, set that equal to 28, what would you get? Well, you'd have 2 times y1 is equal to 28, and immediately we would know something. You would know that y1 is equal to 14. Just dividing through by 2. So we immediately know what the y1 component is. Now just go ahead and take the inner product with the second row in the y vector. Negative 1 will be multiplied times y1, so we're going to have negative y1 plus 2 times y2. 2 will be multiplied times y2. And that will be set equal to what? Well, again, look at the next component in the B vector, it'll be minus 40. But now remember we've already figured out what y1 is in this particular case. So we know that y1 is 14. Okay. So if we solve for y2 here, and I'll simplify just for space here, or use what we had on the previous slide, we have y2 is going to be negative 40. Plus 14, y plus 14, because you're going to have negative times 14, you're going to pull it over to the other side, so this will be plus 14. And that quantity is going to be divided by 2, the coefficient on the y2. If you quickly do that computation, you would get minus 13. So now we know that y1 is 14, we know that y2 is negative 13, and then all we need to do now, take the inner product of the last row here of the L factor and the y1 to y3. What are you going to get? You're going to have y, the combination is going to give you y1 minus y2 plus y3, be a 2 there. I think you can see what that is, even though it's a little bit messy, plus y3 has to be equal to 33. Okay. And again, we know what y2 is right here, and we know what y1 is right there. You can plug them into this equation, solve for y3, and what we would get is y3 is equal to what? y3 is going to be 33 minus 14 and we're going to have, let's see, y2 is going to be minus 13, which will be a positive 13 on this side, but pulled over it'll switch signs, become minus 13. And again, there's nothing in front of the y3 here, so we can just read off what the answer is. There's nothing to divide by 3, and we would get this equal to 6. So what we've determined this far is that the y vector here is really 14 minus 13, 6. Now we're not done. The original problem is to solve for x. All we've done at this point is solve for y. We're not far from getting the solution, because now what we have to do is solve this upper triangular system. But again, hopefully that solution process will be fairly efficient to do. Now we go to solve ux equals y. I've cleared the slide a little bit, and what I've done now is I've gone back and said, all right, what is u? Here's our u matrix. That'll be multiplied times the solution vector we're seeking, x1, x2, x3. But now notice I filled in what y is. We've already determined that y is 14 minus 13, 6. So now just write out the equations representing this matrix times vector multiplication using your inner products. Set it equal to the appropriate component of the right-hand side vector. But again, we know that we can solve for the components of x very simply in reverse order because of this nice upper triangular form. So immediately we'll go for the last component. 0 times x1 is 0, plus 0 times x2, that's still 0. So we'll have 2 times x2, x3 is going to be equal to 6. So immediately you would know that x3 is equal to 3. So what we've determined is we know that the third component of the original solution vector is 3. How do we get the other two? Again, represent your inner products using this upper triangular form. 0 times x1 is 0. So what you're going to have is 4 times x2 minus or plus minus 3 times x3 and that's going to be set equal to minus 13. As we see, that's the component of the y. But now we know what x3 is, so what we can do is then go ahead and solve for x2. x2 will then be equal to quantity negative 13 plus 9. Divided by the 4. And again, negative 13 plus 9, of course, is negative 4 divided by 4. So the second component of the solution vector, the x2 value, should be negative 1. So we're almost done. Now let's do the inner product of the very first row with the column vector x. You'll have 4 times x1 minus 3 times x2 plus x3 has to be equal to 14. And again, we already know what x2 and x3 are at this point. So if we substitute those in, then divide through by 4, we're going to have that x1 is equal to, in parentheses, 14 minus 3 minus another 3 quantity divided by 4. And that will give us the final value of 2. So what we've determined is that our solution vector x, this vector x here, little vector notation there, is actually 2 minus 1, 3. How could you check this? If you take the original matrix A right here, multiply it by that x vector, you should get the right-hand side vector B. So what we've done is we've illustrated if you had the LU factorization or decomposition, sometimes we say factorization, sometimes decomposition is the same. If you take that factorization, you can quickly determine through what we call forward substitution is equivalent to solving Ly equals B, and backward substitution is what we mean by solving Ux equals Y. You can quickly, readily get the solution to the original linear system. Now what we'll do is actually demonstrate how you could derive the solution directly by applying elementary row operations using Gauss elimination, which you've done before in your Math 251 or linear algebra course. Again, LU works wonderfully in terms of if you have the L and U factors provided. But in this case, we're going to just directly operate on the original matrix and derive the solution as you would do mechanically, and then demonstrate how you could produce a Python code to do it for you. Again, what we're trying to do is produce an upper triangular augmented coefficient matrix to derive the solution by preserving the original solution with these elementary row operations. So here's an example of 3 equations, trying to solve them simultaneously. There's 3 unknowns, x1, x2, x3. And what I've done here is I've actually indicated the corresponding augmented coefficient matrix. Again, you have the original matrix A right here with the vertical bar, and then we indicate the right-hand side vector B. And this is an augmented coefficient matrix. Augmented means we've added the right-hand side B, because when we apply the row operations, we apply them all the way across to the right-hand side. Just for the purposes of indexing, I'm going to call the first row A, the second one B and C, just so that we can sort of represent what the operations are. You could actually index them any way you wanted to. Again, the goal here is actually to end up with an upper triangular form here. in the augmented matrix using elementary row operations. The goal in this case is to take a particular diagonal element, like for example the 4 right here, and use that element to produce zeros below it using row operations. The form of an elementary row operation will look something like this, where you would say take any particular equation, say I, and it will be replaced by itself, equation I, minus some multiplier, sometimes we use the Greek letter lambda there, some multiplier, times another equation. So again, we're using equations, this is an I there, equation, say, J. Okay? So this is what's called the pivot equation. Abbreviated equation there. And hopefully by doing that, we produce zeros in the corresponding element that we're wanting to have in an upper triangular matrix. Namely here, we'd love to be able to zero out that element, we'd love to be able to zero out that element, and this one, so that we solely have a upper triangular matrix. So our goal is to produce zeros in those positions. And we can only do that by updating those particular rows, or row equations, whatever you want to call them, by some multiple of another one, right? So what we'll do here is, again, since it's a 3 by 3, the first equation, the A equation, is fine. There's no need. The zeros we're trying to insert have to come in the next two, B and C. So the script, if we're just trying to represent what are the operations that we're going to have to do, is what we're going to have to do is we're going to have to update equation B by itself using this sort of pivot equation approach. This is sort of just prescribing, and then we'll do it. We will take equation B, and it's going to have to be updated, and we need to use some multiplication of equation A to get it. So the question is what combination do we need to take of equation A and add it to equation B, and then and therefore update it to produce a 0 where that -2 is? One way to do it, again, using this pivot equation notation, is to simply take that element -2, divide it by the corresponding element that we use in the pivot equation. So this is called the pivot equation, the A one in this case. We take that element, which is 4, and divide it into the thing we're trying to zero out. Now clearly what this equation really says, what this script really says is that equation B will become equation B, what? Plus 1/2 of equation A. So if you took half of the first row up here, or this equation A we might say, and added it to the second one, B here, you see what's going to happen? You're going to have 1/2 of that 4 becomes 2. 2 plus -2 is 0. It will actually zero that out. These other elements will change too, but the goal was to get a 0 there. Go ahead and write the next one out, and then I'll clear the screen and we'll actually show what the result would be. The next operation would be, well then how do we get rid of that 1? Well, you're going to have to update equation C with what? -1/4. Again, the element you're trying to zero divided by the pivot element. This 4 is what we call the pivot element. Okay? Because it's being used to zero out elements below it, multiplied by equation A. So we use that equation A twice to zero those elements below the 4 out. Okay? What I've illustrated on the screen is the effect of doing those row operations that we were just explaining. Our goal was to zero out those elements below the 4. And in fact, by updating the B equation and C equation appropriately, we in fact have done that. Notice that the elements are all different. The 4, this has all been updated because we take 1/2 of that element and add it to 4, 1/2 of the 1 and add it to the 2, and so forth. And so you can see that the rows are changed past those zeros. But also notice that we use this equation here as what we call the pivot equation. It's used to produce those zeros. It hasn't changed at all. Are we done? Almost. We're not in a complete upper triangular form because what do we need to do? We need to zero out this element here. Again, we have to use row operations. Now the question is what operation, what is the pivot element that we're going to use to produce it? Well, clearly we're not going to use A again, because if we take a linear combination of this row A again and add it to the C row, we're going to introduce something to remove that zero there. It's going to become non-zero. So we don't want to do that. In fact, what we'll use is the B equation now will be used as the pivot. If we write down now the representing pivot equation, what we're going to say is that, all right, then equation C will need to be updated by itself minus, now we need to get the multiplier correct, a combination with equation B. So we're going to fill in what should go for that lambda, the lambda value in the original form we used, or in this case it's called it's going to be the multiplier times equation B. So we're going to use the 3. It's going to be divided into this element negative 1.5. So what we're going to have here is negative 1.5 divided by the 3. And if you simplify that out, because this is negative 1.5, you can easily see that, of course, the negatives are going to cancel out. What we'll effectively be doing is adding, we're just going to simply take half of this particular row and add it to that. If you take half of the 3, that's going to be 1.5. Add it to this element here, that'll get the 0 there, and that's going to do the job for us. Go to the next slide, and now what we see is that we've actually produced the upper triangular form that we need, so that this reflects, the preservation of the original solution. So this is implied that this matrix times x1, x2, x3 equals what this right-hand side is. So let's just write out what those equations really are now. That means that 4 times x1 minus 2 times x2 plus x3 equals 11. Again, because what we're saying is that this row vector here, you could think of the vertical bar there as just reflecting that, we're still preserving x1, x2, x3, and that has to be equal to 11. Similarly, because the 0 knocks out the x1 position, we'll have 3 times x2 minus 1.5 times x3 has to be equal to negative 10.5. And then finally, 3 times x3 has to be equal to 9. Again, I think you've done this in linear algebra class, but it's a good review. If you now just do what we call back substitution in the sense that we will compute x3 immediately, you can see what that's going to be. x3 immediately is going to be 3. Plug that into this equation here at the top there, the middle right here, plug it into that. Solve for x2. Well, we could do that real quickly. x2 then is going to be negative 10.5 plus 3 times 1.5, quantity divided by 3, and that will give us negative 2. And again, if we have x2 and x3, plug it into the first equation. Finishing out our back substitution process, this will give us quantity 11 minus 3 minus 2 times minus 2, quantity divided by 4, that will be 1. So the solution is in fact 1 minus 2, 3. On the next slide, what we see is actual Python code for doing the exact process we did by hand, just to show you how simple and compact we can represent those row-wise elementary operations, determining a pivot, and then modifying the augmented matrix. Couple things I just want to point out in this particular Python code is clearly you're using 2 for loops, one nested inside the other. And we use the range function to get a list of indices that we need. Do keep in mind the meaning of the range function in terms of how it starts and how it's bounded. If we look at the structure here, what K is running over is pretty much all of the columns that are in play, and I is going through the rows. And again, notice with the range function, say for the inner for loop, that means start at position K plus 1 and then run up through K plus 2, so forth, but go up to but do not include n. So this will go up through n minus 1. Okay? Just keep in mind that that second parameter on the range function is a boundary, up to but do not include. Now notice what we're doing here is we on each particular column, of course we're doing 0 indexing. We would start, say for example, in column 0 or the first one, and then run from position 1 to the end of that column. And so we're always advancing and looking below that particular element and on the diagonal, and we're testing to make sure that what we're trying to eliminate is not already 0. So this is just a little efficiency that if you were going to do a pivot equation, for example, I'm just saying if we went back to our 3 by 3 and so you had something like this, and if it turned out you already had a 0 in that position, I'm just going to make something up here, it doesn't really matter. I'm just saying if it turned out that was already, this is part of the augmented coefficient matrix, if this was already 0, then you simply would not want to waste the time to try to take a linear combination with the first equation there to 0 it out, because it already is 0. So that's what this particular code is doing. It's just making sure that what you're trying to eliminate isn't already 0. If it isn't 0, then we want to force the updated form to produce a 0 there. Get your multiplier. That lambda parameter would be the element you're trying to eliminate divided by the pivot, which is some previous diagonal element. And then here's the code to do the row operation that you need. And then we're actually, rather than using A to store both A and the original right-hand side vector B, we're just going to use another, in this case we're using a list to actually, or an array if we're doing it with NumPy, to update that right-hand side. An interesting question to ask is, if you look at this code carefully and realize the fact that it's trying to produce this triangular form, is to say, what we're trying to get this triangular form here, is what happens to the elements that are actually below the diagonal. If you look at this code carefully, we never actually update. We're not actually filling anything in there. We're assuming that that would be 0 and just trying to figure out what happens from the diagonal to the right. So in effect, the elements of the original matrix are still sitting there below the diagonal. So that's what we mean by Aij for the case of I is greater than j. It's all the elements sitting below the diagonal, right? So we don't go back and update those. If you look at how we move across these elements here from position k plus 1 up through n, doing our slices here, you can quickly see that what we're updating is from the diagonal to the end, but we don't actually touch anything. When we're zeroing it out, we're just assuming it got zeroed out. So the original elements of the matrix A are actually still sitting there in those positions below the diagonal. You can find a full, complete module to do Gauss elimination. It's called gausselim.py on page 41 of the textbook, and I'm going to show it to you in just a second. But it's important that you do look at these codes And I will also put these source codes on Blackboard so that you'll be able to access them and not have to copy and paste out of the notes. So I will post any of these modules that we go over explicitly in lecture on Blackboard for your use. I'll probably make a tab for source code and just look for that tab. A nice thing to notice is that it's actually not too difficult to make a change to the code that I'm going to show you in just a second to handle more than one right-hand side. So sometimes in some scientific applications they'll have many right-hand sides, just not a single vector. So it'll be a whole sequence of right-hand sides, and that's where we actually, we would have to repeat bag substitution several times. That's where the LU factorization comes in really, really well, is once you factor that matrix A one time, and actually if you factor it one time, as L times U, then if someone comes in and gives you several linear systems to solve, it's not too difficult to do this LUX equals B, where the B is a matrix of many right-hand sides. So it's very efficient to be able to take the L and U and use it several times. You don't have to do row operations over and over again, like you would have to do in terms of this Gauss elimination code. So if I show you very quickly what the code is in the book, and you can look at that online or in your hard copy, you can see that they have the module Gauss elim, has a nice little doc string that just says, solves AX equals B by Gauss elimination. You can see the function definition. You'll also notice that you can you don't have to provide the order, the size of the matrix. You could get that easily by just looking at using the len function to get the length of that B vector, in this case this B array. We're using numpy. Notice that the syntax for numpy is you could import numpy as np, so that just means you have an alias for numpy, so you don't have to type it out all the time. You can just say np dot whatever function that you want to pull out of the numpy library. It's sometimes handy to do it that way. There's the code that I just showed you on the previous slide, but what I didn't show you is the back substitution code. And here's the back substitution code that will actually use that B array to return the solution. So what comes in is A and B, in terms of A is the matrix, B is the right-hand side, and then what we actually do is update that vector B, or that array B, to be the actual solution. So we're going to override it and return it to the user. Notice it is using the dot product function that's provided with numpy, and this is how you specify the syntax for it. Again, if you say import numpy is np, so the alias for numpy is np, then you can do np dot any function that's available in the numpy library this way. Okay, it's just a handy way of doing it. You're telling the interpreter where this function is coming from. All right. So it's a very nice compact code that you'll be able to use in your next homework assignment, and I encourage you to look over it. Again, the discussion on multiple sets of equations is also provided right after this. It's not too difficult to change this code to handle multiple right-hand sides, so that this B is not just one array, it could be a multidimensional array that could handle multiple right-hand sides.